the Green's function is tantamount to solving the system for an arbitrary force, which is pretty nice, right? I mean, that is what we're after. Here's the nth order case. The nth order constant coefficient case, we'll use Laplace transforms, all right? And so if we take the nth order linear problem, which is this, we take the Laplace transform of that, as we've been talking about the last couple hours of class. Well, the Laplace transform of that just gives me this. Remember, I'm assuming we're looking for the solution with all the initial data 0. So all that pesky y of 0, y prime of 0 terms, those are gone, just like in my example 1 and 2 today. Okay? And so this gives me the characteristic polynomial in S times y of S is equal to the Laplace transform of big F of S. Right? So what? So then we solve for big Y, right? And y of t, what's my solution going to be? It's going to be the inverse Laplace transform of 1 over p of s times f of s. Right? Now, p of s is the characteristic polynomial for the system. For the one we just worked, this p of s was s squared plus 6s plus 9. 13 plus 13. And so here's what you guys do in engineering. You define the, this h of s, the so-called transfer function, to be 1 over p of s. So the transfer function is completely governed by the part of the system which is not from the forcing function. It's the homogeneous part of the system, if you will. The L, basically. L fixes what the transfer function is. Why do we call it the transfer function? Well, let's see why that is. You know, so this is, again, the solution would be the inverse Laplace transform of the transfer function times f, 1 over p times f. And, you know, my larger program is that, well, we can write that as the integral of Green's function, whatever that is, times f. Well, what is Green's function? How does Green's function, this k, relate to the transfer function, 1 over p? The answer comes to us through something called convolution. Convolution is a very peculiar way of combining functions. The convolution of f and g, all right, is the function such that the Laplace transform of the convolution is the product of the transforms of the convoluted functions. In other words, if we take the inverse Laplace transform of the product of two functions of s, it will give me back the convolution of the inverse transforms. This is really, really nice, because this means we can take inverse Laplace transforms of things without doing partial fractions. We can actually just take the convolution of them. For example, can you hit the lights for a second, King? If I wanted to take the inverse Laplace transform of the thing we just worked on, 1 over s times 1 over s squared plus, 6s plus 13, what this convolution product is saying is that this would be equal to the inverse Laplace transform of 1 over s convoluted with the inverse Laplace transform of 1 over s squared plus 6s plus 13. I hope you can see why that's valuable, because these are straightforward to find. But then the devil's in the details. What does this mean? What is that, this convolution product? What is that actually? There must be a cost. There is. You turn the lights on. So what the cost is this. Oh, we'll get back to the cost in just a second. Suppose it exists. If it does exist, then the inverse Laplace transform of the transfer function times f of s will be inverse Laplace transform of the transfer function times the inverse Laplace transform of the Laplace transform of the force, which will be the convolution of h and f. F is the given forcing on the system. H is the inverse transform of the transfer function. And so that gives us a clear path to constructing Green's function also. So here's a hand-wavy, very hand-wavy derivation of the convolution. I want the convolution, the Laplace transform of the convolution, to be the product of the Laplace transforms, all right? So then you do this. You make an incredible jump to combine the integrals like so, and that becomes e to the that plus that. Then make a substitution like so. Pull this out. Keep that. But this is, anyway, here's a hand-wavy derivation of the formula. The thing at the end there is actually the convolution of f and g. So through these sketchy arguments, this just assumes what I want. And here's some questionable integration. And it derives this formula right here. The convolution of f and g is the integral from 0 to t of f of t minus u g of u du. So what I was saying over here all of a sudden seems less nice, right? Like partial fractions is just algebra. This is an integration. This, which is not impossible, but it comes at a cost, right? I mean, it's integration. Now, there's a careful proof of this on page 400 of the text, okay? That it actually satisfies the convolution property. Convolution has nice properties. Convolution of 0 and anything is 0. The convolution has, you can pull constants out. You can break up across addition. It's also commutative, which is not entirely obvious. Here's the proof. Convolution of g and f is this, but we can make a w substitution to get that, which gives me that, which is f convoluted with g. So it's also symmetric, which is, commutative, which is kind of important. In associativity, you could prove, I won't do it. All right, so what do we got? So the nth order constant coefficient problem, L of y equals to f, we can rewrite this as a polynomial in the differentiation operator times y equals to f. We take the Laplace transform of this. This gives us that when we take the Laplace transform of that, what we get is p of s times y of s. You divide by p of s, that gives me a big Y, 1 over p of s times f. This is called the transfer function. And then to solve for little y, all I have to do is take the inverse Laplace transform. Here it is. And the convolution does that. Convolution is a thing that I can do that will take the inverse Laplace transform of a product and write it as the product of the inverse transforms, but the convoluted product. And so there it is. And then this is by definition of that. And now you can see that h of t minus u is precisely the Green's function for the problem. So the Green's function is related to the transfer function. It's the inverse Laplace transform of the transfer function at t minus u. But I'd like you to notice that we have just derived the inverse to the differential operator for an arbitrary nth order problem. That's what Laplace transform's done for us. It's quite beautiful. And finally, how do you build the solution to a system? Well, to get a solution to the system which doesn't necessarily have initial data being 0, well, that's all taken care of by the homogeneous part. See, if I add in the homogeneous solutions, I can choose C1 through Cn to make whatever initial data I want non-zero, right? And then this piece over here gives me a particular solution which has all of the initial data 0. So this is a completely general solution that will reproduce the force when we plug it into L. And this, we can adjust the C1 through Cn to fit whatever initial data we happen to have. And then to round it out here, what I do is I actually calculate the transfer functions for a few pretty common examples. For example, if we had the characteristic polynomial being distinct real roots, so this would be something like, for example, y prime prime plus 3y prime plus 2y would be an example like this. If you have that's the transfer function, we do partial fractions, you get this. So your h of s looks like that. The inverse transform is this. And when I take the convolution of h of t with f, I get this. And there you go. That is, in fact, the Green's function for this problem, derived by this convolution method. Here's a specific example. Oh, look at that. Y prime prime plus 3y prime plus 2y. That's funny. That's what I said a minute ago. I was just making one up. It's an accident. Anyway, so for this example, if you use this technology, the the transfer, the inverse Laplace transform of the transfer function is that. So when you take the convolution, we get this with that, and you do this integration, and there's the solution. Now, am I advocating that this is how you should solve problems on the final? No, I am not. What I'm trying to introduce you to is this wild world of linear systems theory. And this is a way of thinking about systems in general as being some kind of operation L. And what does L do? Well, it responds to a force which is put on it, right? And the output is the solution. And L inverse is the opposite of that, which we can build with Green's function. So, and here's the Green's function for the quadratic case. But I think that's it I got in here. Here's the repeated root one. So anyway, you guys can look at this. I'll show you where I found it, if I can find it. Where'd that thing go? So on the web page, right? It's right under useful material and links. It's this guy, concerning the connection between Green's functions and the transfer function. A lot of this I got from Finney and Ostberg's fantastic book, which is really hard to find in print these days. But anyway, you can hit the lights again, King, if you don't mind. Thanks. Yeah.
Sorry, this is unrelated to this, but did you
Go for it.
saying that classes after this were canceled? My RA just told me. I just want to make sure it's real. No way. Sorry.
I would feel so vindicated. I called it. 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 I canceled that class this weekend. Ha ha. Ha.